Hello, Mr. Area, alright? Okay, so today we talk about the binary tree. Okay, I will draw a binary tree. Okay, here. 10, 5, 10, 2, 3. So this is the binary tree. And how many ways if we want to remove one edge from this binary tree? How many ways? Okay?
4.
Four edges, 4 possibilities. So what happens if I remove one edge? What happens? What do you get? What do we get?
2 trees.
2 trees. We remove one edge, yeah? Remove one edge. One edge. 2 trees. 2 trees. 2 binary tree, yeah? Binary tree. What, if it's 2 binary tree, what do we also call it? What do we also call it?
Forest.
Forest, yeah. Okay. Forest. This is the concept. So if I removed one edges, and we want to find out if it's possible that for these 2 binary trees to have the same total sum, okay? So for example, in this case, if I remove this edge, what happens? The sum of these, 15, and the sum of these, 15, yeah?
Yeah.
Okay, if it's not possible, we just remove, for example, this is 1,000, then apparently it's not possible, then we just return false. Okay, so given the binary tree, do we still remember how do we calculate sum in the recursion, the depth of search? Remember? Define the sum, yeah, the depth of search sum, depth of search. If this is the root, okay, so it's very easy, right? Can you tell me? If not root, if root is empty, what happens? What should we return? The sum.
Sum.
Return what? If the root is empty, what's the sum? What's the sum of the root empty? Come on, if it's nothing, what should we return? The sum of the root.
0.
Yeah, come on. Otherwise, we do what?
I've always.
Yeah, depth of search what? And look, this is a tree. Yeah, this is a tree. This is a tree. I don't care, right? Something here. This is a tree. It has the left tree and right tree. And if it's not empty, the sum of all of these equals what? Equals root of value is this one. Plus, what's this bit? What's the sum of this bit?
Under 10.
No, it's not binary search here. I'm talking about, now I want to calculate the sum of this binary tree, right? If it's empty, I return 0, which is the base cases. If it's not empty, and it equals the sum of this bit, yeah, which is 10, yeah? Wait, look at me. And what's this bit? What's this bit? Recursionally, what's this bit and what's this bit? Plus what? Plus what? Plus what?
Read the left, read the right.
What do the left? Come on, what do the left? Depth of search, because we're calling itself to solve, to get the sum of the left tree, yeah? And then depth of search, root of right, right? Right? And then return as, yeah? This is the, we have used this before to compute the sum, yeah? The sum of the binary tree, yeah? Binary tree using the recursion, depth of search, right? Okay, so if I put the sum, okay, so based on this, let's do this tree again. So if I have a scene which stores the number of the sum we have seen so far, okay? So what do you think it will contain, the scene? If I put it here, scene dot append s, what do you think? What we get? What do you think? What we get? Pay attention. Come on. If this s, return s. What's this s? This is the sum of any subtrees, any subtree including itself in this binary tree. Yeah? And we want to recall. We want to remember scene dot append. We want to push the sum to this. So, how many subtrees are there? How many subtrees? How many subtrees are there?
5.
What are the subtrees? 2? Yeah? This is a subtree, yeah? 3?
Yeah.
And what else?
10.
Why is it 10? subtrees, including the left tree and right tree, because look, S is the root of value plus the sum of the left tree and sum of the right tree, right? Right? So 2, 3 is a subtree. 10 plus 2 plus 5, 3, yeah? This is a subtree, yeah? You need to pick all its children, right? Descendants, right? So this is 15. And what's the subtree of this one?
30.
30. And what's the subtree? Any other subtree? Is this a subtree 5?
5.
Yeah. Okay, so after this, we got this, right? Yeah? And we want to remove the 30. 30 is actually the last one, because when you do this recursionally, the last, which value is the last S? Which value is the last S? I append this. So if I call DFS root, what do you think? What's the last value of S? DFS root. What does DFS root return?
It returns the
the sum of the whole tree, right? And the sum of the whole tree, since the append S, so the last element will be the sum of the whole tree, which is 30, right? Yes? Am I right?
Why does it minus 5?
No, okay. Okay? So look, this is 30. And what's the half of it? If
15.
That's right. Okay, so look, this whole tree, the sum is 30. And if I split into 2, and if they are equal, what's the sum of that half?
The deficit root divided by 2.
Yeah, I know that 30. Now I know this is sin minus 1, right? Right? I know this is as sin minus 1. If I divide it by 2, I mean, what's the sum? What's the sum if I divide by 2 if both trees are equal?
Will be 30.
Divided by 2, 15, right? If I get rid of these, and I want to know if there's a tree, if there's a number in the rest which is equal to half of 30. Got it?
15.
Yeah, if it is, then we find a solution. Got it? Does it make sense? Yeah? Then it is.
How about the other ones?
What do you mean the other
The
one?
other 3.
5
And 10.
and 10.
Yeah, how about that?
Yeah. Look, 5 and 10. This is 15. How do we get a 15? It's 10 plus 2 plus 3. Right? And then you cannot pick 10 and 5 to get. You need to pick 10. If there's a left tree, you need to pick it. And if the right tree, you need to pick it. That's why look, S equals root of value plus the left tree plus the right tree. The sum of the left tree and the sum of the right tree. You need to, the whole subtree. You cannot just pick these two and we ignore the right subtree, right? Because it's there. And then we append all the possible subtree sums into S. Right? And the last one is the subtree, is the sum of every node. If we do this S, look, if these, let's do this step search, and then S dot pop, right? If do a T equals that, S dot pop. S dot pop, we remove the last one, which is the sum of all subtree, right?
Mm-hmm.
And then we just need to find out if the rest, if T divided by 2, yeah? Everybody look. If T divided by 2 in what? In this scene, right? Got it? If it's in the scene, if it's in the scene, it means that we can find a way to split the binary tree into half, and both have the equal sum. Okay? Okay? Does it make sense?
Mm-hmm.
What's the time complexity? Yeah, because we need to visit what?
All of
Every node, yeah? What's the space complexity?
N.
Yeah, why is that?
Scene.
Yeah, good job. And also we're gonna stack, yeah? Stack. Recursion, okay? Got it?
Yeah.
Okay, can you explain to me how do we solve this? Just make sure you understand.
Well,
Yeah?
yeah, and so we just
Sorry, yes? Can you be quiet? Yes?
We're just adding all of, we're just doing all of the subtrees.
Subtree sums into the scene, yeah?
And you know the depth of search root,
Yeah.
which is all of them, you just divide it by 2 and see
If it's the,
yeah.
If it's in the, if there's a subtree sum which equals to half of the total subtrees, what does it mean? What does it mean?
It means it's true.
It means, yeah, it's true. There's a way to to remove one edge, split the binary tree into half, right? And then we can find out the subtree sum, right? Yeah, because this method is quite elegant, right? It's quite elegant. Otherwise,
It's
what?
not beautiful.
Sorry?
It's not really beautiful.
Beautiful, yeah, good job. Beautiful algorithm, yeah, good job. Look at this, we already know this, right? I mean, maybe 100 days ago, we already learned the recursion to compute the sum of a binary tree, right?
100 days ago.
Probably, you know, look, base case, if it's empty, return 0. Otherwise, what's the sum? The sum of its node, and then we do recursively solving the left tree and the right tree and put it together. Return S. All we do today, scene, and we put all the possible sums, subtree sums into the scene. And the last one will be the sum of all the nodes. We do move this bit, and we compute the half of it, right? If it's half of it, if half of it is in the list, then there's a way to split it into two, right? Easy. The time compressed OM because we visited all the nodes. The space compressed OM because we use the scene, we use the stack, yeah? Okay? That's it for today. Good job!
Bye!